Following the same process, now we consider the reflection properties of Tm wave from the plane dielectric boundary. And we first define the EH field of the incident field. Yes. And for Tm polarized the incident wave, we have the Y field in the Y direction. And the E field, we have two components, S component and Z component. So are the reflected wave and the transmitted wave. And in medium 1, the total E field is the incident wave plus the reflected wave. The total H field is the incident wave plus the reflected wave. So we can define the characteristic of the Tm wave in medium 1 as it propagates with an angle θ1 to the normal vector. We will have capital Z01 is eta1 times cosine θ1. Let me remind you that for TE wave, the characteristic impedance in medium 1 is eta1 divided by cosine θ1. But for Tm wave, the characteristic impedance is eta1 times cosine θ1. Okay? And in medium 2, we can also have the characteristic impedance Z sub 01, which is eta2 times cosine θ2. And we have also defined the wave impedance for Tm wave. The wave impedance for Tm wave is capital Z is Ex over Hy. Okay? So the definition of wave impedance for Tm wave is in this form. And remind you that for TE, the definition for wave impedance is minus Ey over Hx. Okay? So following the definition here, we can then use the continuity of the wave impedance at the dielectric interface. Then we can obtain the reflection coefficient gamma for Tm wave from the plane dielectric interface. It will be Z sub 02 minus Z sub 01, which is divided by Z sub 02 plus Z sub 01. The definition for the reflection coefficient for Tm and for TE, they are the same. Okay? But the Z01 and the Z02 for TE and for Tm, they are different. So take the Z01 and the Z02, here should be 2, for Tm into this equation. Then we can have the reflection coefficient can be written in the following equation. So this expression is the reflection coefficient for TM wave from the plane dielectric interface. Since we have learned the reflection coefficient for TM wave from the plane dielectric interface, now we would like to know what will be the so-called Brewster angle. The Brewster angle is defined as the incident angle which makes the reflection coefficient gamma to be 0. So if you have an incident angle and at this incident angle you will have no reflection, then such angle is so-called Brewster angle. And as I have mentioned, for TE wave, there is no situation for gamma is 0. So for TE wave, there is no Brewster angle. But now, let's check if the TM wave has the Brewster angle. So to have the reflection coefficient gamma to be 0 for TM wave, let's go back to the previous slide here. The reflection coefficient for TM is defined here. To have the gamma to be 0, we must make this part to be 0, right? So setting this part to be 0, we will have one minus sine square theta 1 will equal to the following terms. Okay, and if we can satisfy this condition, then we will make here to be 0, then we will have no reflection. As a result, to satisfy this condition, we consider the normal case, that is, if there is no magnetic material. So for non-magnetic material, we will have mu1 equal to mu2, which is mu sub 0. Okay? Then, for non-magnetic material, the above condition can be rewritten as can be rewritten in this way. Then we will have the tangent theta 1 can be expressed as the square root of epsilon 2 over epsilon 1. And we know that epsilon is in proportion to the square root of epsilon is in proportion to the material index. So this part can also be written as N2 over N1. That is, if we have the incident angle theta 1 is arctangent N2 over N1, then we will satisfy this condition for non-magnetic material. and then we will have gamma to be 0. That is, we will have no reflection. Okay? So such kind for this incident wave, incident angle, for this incident angle, we call it Brewster angle, which is also written as theta b. So please remember that the Brewster angle, we only have Brewster angle for TM wave, which can be can be obtained by arctangent n2 over n1. Okay, please remember this. So the figure in the right hand side show you the reflection, the power reflection for the T wave and the TM wave incident to the plane dielectric interface with the material index defined here. And clearly you can see that for such kind of situation, we have plane dielectric interface, and in the above is N1, which is 1. Below here is N2 is 1.52. And from the material index N2 and N1, we can find out the corresponding Brewster angle for TM wave, which is 1.52 over 1, and we can have it is about 56.6 degree. Okay, so for the reflection, power reflection, you can see the blue curve here represents the power reflection for T wave, and as you see, there is no C.1, which make the reflection to be 0. But however, for TM wave, which is the red curve, you can see that around this angle, there we will have no reflection. This is because the reflection coefficient is 0. Okay, so this angle is just the Brewster angle we have calculated here. So here is the Brewster angle for TM wave from the plane dielectric interface.